Hello there, everybody. Welcome to episode 19 of Math 141 Summer 2020 Recitation. We are here doing our final exam review. I cannot believe that the end of the semester is so very close. It really has flown by. I knew it was a short course, only being, 6 weeks? But even so, it has flown by. It is true what they say, time flies when you're having fun. So we're doing the exam review today. Even though there's 2 more sections left to cover, simply because of the way the timing works out. But this should give you plenty of good preparation for the majority of the class, and then we'll have videos out the next 2 days focusing on the remaining 2 sections. So what I've done for today is I have gone through all 3 of the exams, including the one which technically is still open as I speak now. It will close in about an hour and a half. And I have essentially pulled out the most challenging problems in terms of the scores of which you all received. And we're going to go through and do some of these problems. I've got 6 of them. And hopefully this will help get you in good shape for the final exam later this week. So here we go. I'm not going to tell you anything about kind of what section, or maybe I'll mention it in passing, but I'm not going to number these problems or tell you in advance what section they are from, because on the final exam, or in general, when you're out in the wild doing math, you're not usually told very nicely, oh, look, you have to use this rule here. It is up to you to identify that. So that's what we're going to do here. So let's just call this first problem, problem 1. And this is an application. So we have that the half-life of a certain radioactive substance is 24 hours. There are 17 grams present initially. There are 17 grams, not that kind of gram, not like a graham cracker, you silly goose. Like the weight, grams, present initially. Okay, so that is the setup. We've got 2 parts to this problem. I think that the first part will probably be a bit more challenging, but we'll see. Actually, I think they'll both be fairly straightforward now that I think about it. Part A asks us to express the amount of substance remaining as a function of time and this is going to be an important detail in days. Okay, so they want time to be in days, and we're going to call that t. So let me emphasize again. Oh, let me try out this highlighter. In days. Oh, look at that. Isn't that nifty? In days, okay? So that's an easy place, especially on a take-home or an online exam where it's difficult to get partial credit. That's an easy place to make a small mistake because we are given, notice, we are given time in hours in the initial problem. So we're going to have to make a slight conversion there. Thankfully, 24 hours in 1 day is a fairly straightforward conversion. So here, we're going to use a nice formula, which is given in your book. Assuming you've done these homework problems, I'm sure you recognize this kind of problem. So hopefully the formula is going to ring a bell for you. So if y naught, okay, y sub 0 or y naught, there are different ways of saying the same thing. If this is the amount of substance present initially, okay, so an amount of substance present initially, then the formula, then y equals y naught times e to the kt, to the minus kt, gives the amount of substance present at time t, amount of substance present at time t. And you'll notice I haven't yet defined what K is here, where K, and this will be a general formula, well, yeah, where K is going to be ln of 2, the natural log of 2, over the half-life. Over the half-life. Sorry if you heard that little smack. I had a bug. There are all these little flies around here nowadays in the summer. I heard that that's a thing here in Colombia. Okay. So this is the setup. Now we're going to go ahead and plug in all of our information. Well, the amount of substance present initially, we are told, is 17 grams. Okay, so we have that y naught equals 17. Now the half-life, we are told, is 24 hours. Remember, we want to convert that into days. And so we get then that K is equal to ln of 2 over, well, half-life, it looks like we're going to use 1 here because, again, 24 hours equals 1 day. Well, that's nice and simple. That's just ln of 2. So let's go ahead and plug this into our formula. We have y equals y naught times e to the minus, okay, so we had e to the minus kt. Let's go ahead and write that, and then we'll plug stuff in. Okay, so that's 17 e to the minus ln of 2 times t. And we could, in theory, leave it like this, but I think that we can make this much more easy to work with if I do the following. So let me rewrite this exponent here as e, put it in parentheses, e to the minus ln of 2 of t. Okay. Remember, whenever I multiply exponents together, I can do this. This is legal. These two things are the same. Okay, well now, because of natural log rules, I can bring that negative in front of the natural log and write that as ln of 2 to the minus 1 to the t. Okay, I'm showing way more steps than you would need to. You could skip some of this algebra if you wanted to, but I just want to be crystal clear here about everything that's going on. So now I can replace that 2 to the negative first with just a 1/2. And the great thing about this is that you will recall, this is another good fact which you should be aware of come final exam time. Well, for any constant a, e to the natural log of a is just a. In other words, the e and the natural log kind of cancel each other out. In particular, in this case, we see that that gives us 17 times 1/2 to the t. And to be fancy one more time, 17 times 1 over 2 to the t. Okay, 1/2 to the t, that's just 1 to the t over 2 to the t. And 1 to any power is just 1. So this numerator is really secretly it's 1 to the t. But 1 to the t is going to be 0 no matter what t, or going to be 1 no matter what t is. So this gives us our formula. Okay, so this is the amount of substance remaining as a function of time, right? We can see that this is dependent only upon t, which is time. So this gives us what we are looking for. Part B asks, when will there be 2 grams remaining? Be 2 grams remaining. So we probably didn't have to do quite all that simplification in the previous problem. I mean, you'll notice really at this point we had already plugged everything in. So really everything after that was just simplifying. One advantage of that though is that now that we're going to have to do some computation, we're gonna have to play around with this formula a little bit, we will have already made our life a little bit easier. So when will there be 2 grams remaining? Well, in general, the way that we're going to do this is we are going to set 2 equal to our formula for amount of substance remaining. Whenever we do that, we're then going to want to solve for t. Okay, so in particular, let's go ahead and write it out in this case. So I've got, remember, y up in our formula above here, above part B. Remember that y represents the amount of substance remaining. So I'm going to set that equal to 2 because I want to know when there are 2 grams. So 2 equals 17 times 1 over 2 to the t. Now we're going to solve for t to find the corresponding time. So, oh boy, let me see. Let me divide both sides by 17. This is just going to be some algebra. There's going to be one cute little trick at the end. Okay, so I've got this. Now, I can flip both sides of this. So this means that 17 over 2 is 2t, to the t, excuse me. So now I need to get that t out of the exponent. Okay, remember, so to get t out of exponent, you remember what trick we're going to use? We are going to use the natural log. Natural logs are always wonderful for helping us get exponents out of variables. So if I take the natural log of both sides of this thing, then I get ln of 17 over 2 was ln of 2 to the t. Well, kind of like we did earlier. So earlier, you'll recall that I had this negative out front, and I brought the negative out front into the exponent, right? I brought the negative 1 out front here of the natural log as an exponent. Now we're just going to do that in reverse, and I am going to bring that exponent, that t, down front, ln of 2. And that is the beauty of it, is that now I have ln of 17 over 2 over ln of 2 equals t. We might be able to simplify the left a little bit if we wanted to, if we play around with some fancy logarithm rules. But I think that this is perfectly fine. In fact, the problem says on the computer, round to the nearest hour as needed. So I would use your 4-function calculator, which you should have handy for the exam, and punch that in, and then round it to the nearest hour. Keeping in mind that t here is given in days. Okay, so whenever we solve for hours, the problem is asking for hours. We're going to need to do another quick conversion. So this will give us the time in days. So then we're going to have to divide that by 24. Or excuse me, divide that by 24, right? No, we're going to want to multiply that by 24. Yeah. So this gives time in days. This gives t in days, and then the problem asks for hours. So multiply by 24 for the hours. Yeah. Okay. Good stuff. That is the first problem of the day. That problem, if you were wondering, it is problem 1.6.81. So I suppose I'll go ahead and write it up here. 1.6.81. That is where that problem came from. Now, let me go to the second problem. Give me just a second. Normally I have all of the problems up right in front of me because it's all coming from the same homework assignment, but now I'm jumping between exams. Oh yes, related rates. Okay, we have a related rates problem here. In fact, I think that we did this problem, or a very similar one, in a previous recitation video, but it is certainly worth revisiting as this is a tricky one. So a ladder is leaning against a house, when its base starts to slide, away. Away, okay. By the time the base is 6 feet from the house, by the time the base, is 6 feet from the house, the base is moving away. At the rate of 16 feet per second. So we have two parts to this problem as well. So part A is asking, what is the rate of change? I should go ahead and sketch the picture, actually. So let me go ahead and sketch the picture. Thankfully, they give us a picture here, which makes our life a little bit easier. Okay. So let's see. So this is the y-axis, x-axis. Okay, so let me sketch my ladder. They have it like a little rectangle, but it doesn't really matter. All right, so let's see. We've got a lot of things labeled here. Among them, so we have this angle here. This is called theta. Okay, everybody say hi to theta. Hi, theta. This length here is called x of t. Okay, this is a function of t because the ladder is sliding, right? So this is changing as this length is changing as time changes. Similarly, this height here is called y of t. Okay, so remember that height is changing based on time as well. And we recall that the ladder is 10 feet. Or in other words, the length of this thing is 10. Okay, so that's the picture that we're given. Now let's go ahead. I suppose I should label this as 0, just because the picture does. Okay, so let's go ahead and write out part A of this problem. The rate of change, this is a 3-parter. The rate of change of the height of the top of the ladder. Of the height of, rate of change of the height of the top of the ladder. I realize now what is the rate of change? That is the question. What is this rate of change? The rate of change of the height of the top of the ladder. Okay, well, let's go ahead and see what the heck is this even asking for. So the height of the top of the ladder, well, that is given by y of t, right? The height is this quantity on the left here, which is given by y of t. And we want the rate of change. So we want to find dy dt. Okay. And in fact, we are given a couple of values, right? So we're given that by the time the base is 6 feet from the house. Okay, so we can actually, let's leave it for now. So we want to find dy dt. So why don't we go ahead and start by writing out some equations. Okay, so I don't know exactly what dy dt off the top of my head is, but I bet you that we can draw some information out of this picture that we're given. So the first thing that I notice is that I can use the Pythagorean theorem. So Pythagoras says that x of t squared plus y of t squared equals, well, it's going to be the length of the hypotenuse of this right triangle squared. And the length of this hypotenuse is going to be 10 because that's the length of the ladder. Equals 10 squared, and that is just 100. Okay, so now what I'm going to do is I'm going to take the derivative of everything with respect to t. All right, and what I find is that, so let me see, so this is going to be 2x of t dx dt plus 2y of t dy dt equals 0. When I take the derivative of 100, it just becomes 0. All right, so this is what we got. We can rewrite this as follows. We can rewrite this as 2y of t dy dt equals negative 2x of t dx dt. Let me see, I can divide by 2 and I can get y of t dy dt equals, let me see here, that's going to be just a negative x of t dx dt. Okay, now if I divide over y of t, this is going to give me dy dt equals negative x of t dx dt over y of t. Okay, so now we got a nice formula for dy of t, but we still have a few variables which we need to check in on. For example, so we need to solve for x of t, dx of t, and y of t, or excuse me, dx dt, that's what I meant whenever I said that. Some of them we might need to solve for, and some of them might be given to us if we read carefully. So let's just go in order. So it looks like x of t comes first. Let's figure out what that is. Well, x of t, we are told that the length of the base, by the time the base is 6 feet away from the house, so this gives us our x of t, because this is saying this is the length of this, the base of this triangle here. Okay. So x of t is just 6. How about dx dt? Well, dx dt, so the rate of change of this base, well, it looks like by the time the base is 6 feet away, the base is moving away at the rate of 16 feet per second. So that gives us our dx dt because that's telling us how fast this base is sliding away. So dx dt is 16. Okay, so let's find y of t now. Hopefully this will be given to us. And unfortunately, they don't quite give us it explicitly, right? I don't see it anywhere explicitly in the problem. However, we do know from our boy Pythagoras that x of t squared plus y of t squared equals 100. So let's jot that. Let's jot that down here. So x of t squared plus y of t squared equals 100. Well, this is the same as saying y of t squared equals 100 minus x of t squared. Well, this is the same as saying, if I take square roots of both sides, y of t equals the square root of 100 minus x of t squared. Now, normally whenever we take square roots, we need to worry about negative solutions, right? But here, there's no need to worry about negative, to worry about I'll just write it this way, about negative square root. Because y is the height, because y of t is always going to be greater than or equal to 0. Right? This ladder, certainly the height is never going to fall below 0. Right? That doesn't really make sense in this context. So that's why we only care about the positive square root. So I promise I'm not being forgetful in that case. Well, we know x of t is 6. So this means that y of t is the square root of 100 minus 6 squared. And that's the square root of 100 minus 36. Root 64, and that is 8. 6, 8, 10. One of the classic Pythagorean triple. All right, so now we see that y of t equals 8. So now we have all of the variables that we need to solve for dy dx. So we see that did I write dy dx? Shoot, that's a bad habit. Well, it's not a bad habit because normally you are writing dy dx. It's a bad habit in that, in this case, I almost made a notation. Well, I did make a notational mistake, but I was able to fix it. Okay, so x of t, I'm sure that you were yelling at me through your computer screen, so thank you for catching me. All right, so we're going to plug in our values. So I can have negative x of t, so negative 6, times dx dt, which we said was 16. And then we just found that y of t was 8. And is it squared? No, it's not squared there. And so this, well, let me see. Negative 6 times, well, 16 and 8, that cancels out to just become a 2. It looks like we have negative 12. So that is dy dt. And if we look at our picture real quick, it does make sense that y of t should be negative because as time goes on, this height is getting shorter, right? This ladder is getting closer and closer to the ground. So the height is getting smaller, meaning that it's decreasing. So it makes sense that dy dt is negative. Okay. Oh, I shouldn't have drawn that line because there's a part B here. This video could very well go a little bit long, but I'm okay with that. I do want to get these, problems in so that you are as prepared as possible for the exam. And I want to get them in detail. So at what rate is the area of the triangle formed by the ladder wall and ground wall and ground changing then. So whenever they say then here, they mean when x of t equals 6. That's what they mean by then here. At what rate is the area of the triangle formed by the ladder, wall, and ground changing then? Okay, well again, the first thing that you want to do in a related rates problem is identify what in the heck do you even want from me. So in this case, we want to find the rate of change of area, okay, area of the triangle. We want dA dt, where A is what I'm going to call area of triangle. That's a bad triangle. Okay, that's clever. That's better. Okay, so we want dA dt, for A is the area of the triangle. We wrote a few nice and fancy formulas up here, right? We mostly this one due to Pythagoras, your boy. But we don't have anything which gives us the area right now. So the area of the triangle, let's go ahead, I'll just jot it down right here. Well, we have the picture in front of us. The area is going to be given by, it looks like it's going to be, so in general for a triangle, it's 1/2 base times height, right? I hope that looks familiar. And in this case, the base of the triangle is given by x, and the height of the triangle is given by y. Okay? that's our area formula. Let me copy that down here. So area equals x of t equals 1/2 x of t y of t So if I take the derivative of both sides with respect to t, okay, so then I'm going to get, so this means that dA dt, in fact, I think I made a mistake here whenever I did this problem in the first time I did this in a video. This is going to be 1/2, and now I'm going to have to hit the second part here, this x of t, y of t with product rule. I think I forgot to do that the first time that I did this. So let's see, I'm going to have x prime of t. Let me write it this way just to be consistent with our notation. Let me write it as dx dt times y of t plus dy dt times x of t. Okay. So it looks like, again, we're going to have some variables, but I'm pretty sure that we've already solved for all of them. So let me see, 1/2. Okay, dx dt, we used that in the last one, and dx dt was 16. So it's going to be 1/2, 16 times, okay, now y, we need to find y, and y came out to be 8. Okay, so that's going to be 1/2, 16 times 8, plus, okay, dy dt, that's what we solved for in the previous problem, and that was -12. So plus -12, and times x of t, and we're in fact given that we want this at x of t equals 6. So times 6. And now we just go big brain. This is 1/2. Oh, yeah, okay, that's fine. 1/2, 16 times 8, well, 16 times 4 is 64. So this is going to be 2 times that, which is 128. 12 times 6, that's -72. This is 1/2, 128 minus, that's 46. And this, no, 56. Thank you. I'm sure that you caught that. 1/2 times 56, and that is 28. And hang on a minute. What happened? I accidentally slid to the top. Change in area. Okay. All right. So that gives us our second problem. So this is dA dt. And finally, part C. Part C asks, at what rate is the angle between the ladder and the ground, between the ladder and the ground, changing then. Again, by then they mean when x of t is 6. At what rate is the angle between the ladder and the ground changing when x of t is 6? Well, going back up to our picture, that angle, we gave it a name. That angle, we named it theta. Okay, it's got its own little cute little birth certificate. So that is angle theta. Now this is a little bit trickier, but what we can see, well, we see that tangent of theta, it looks like tangent of theta is going to be given by opposite over adjacent, so called TOA. Tan theta equals y of t over x of t. Right, that gives us a nice formula for theta. Okay, so let me run down back here, and we'll jot that down. So here we want d theta dt, and we just found, well, we found that tangent of theta was y of t over x of t, which means that to solve for theta, if I take arctangent of both sides, then I'm going to get theta equals arctan y of t over x of t. Okay, so we need to take the derivative of this with respect to t. So d theta dt equals, okay, this one on the right is going to be a bit tricky, but we're going to get through it together, okay? So recall, this is a tricky derivative, but it's a good one to know for sure, that the derivative, let me use a different variable because, man, we've already used so many variables. I'll just call it x. The derivative of arctangent of x, you'll recall, is 1 over 1 plus x squared. So in this case, we're going to have to use the chain rule. So the first thing we're going to do is we're going to have 1 over, and then in our denominator, we'll have 1 plus, and then whatever is on the inside, we want to square it. So y of t over x of t squared. Now we need to multiply that by the derivative of y of t over x of t. And for this, I need to use quotient rule, right? So for this, I'm going to have dy dt times x of t minus dx dt times y of t all over x of t squared. Okay, and again, this looks fairly messy, I'll admit. It's not the cutest, but it is all information which we have. So we can go ahead and just plug in some values. 1 over 1 plus, okay, y of t was, we're going to have to go back to all these things that we computed. So y of t was 8 and x of t was 6. Okay, so let's go ahead and put that in here. So 8 over 6, and yeah, we can simplify that. Times, okay, dy dt, I believe we said that was negative 12. Yep. Pardon my very quick scrolling. All that I'm doing is going back and referencing our earlier values. So negative 12 times 6, x of t, minus dx dt we said was 16. That was given to us, in fact. And then y of t is 8, so 16 times 8, over x of t squared, so it looks like that is 6 squared. Let's go ahead and knock this thing out real quick. So that's 1 over, I'm going to do some quick algebra in my head, 1 plus 16 over 9 times negative 72 minus, that's 128 over 36. So this is, well, 1 plus 16 over 9, that's 9 plus 16 over 9, so that's 25 over 9. So if I flip it, that's 9 over 25. Times, okay, well, negative 72 minus 128, that's minus 200 on the dot over 36. We can do some good old-fashioned canceling. 9 over 36, that just becomes 1 and 4. And then 25 and negative 200, this just becomes a 1 and an 8. So it looks like I just have negative 2. Ta-da! It's possible that I made a small mistake somewhere in here. So I apologize if there's a small numerical error. But in any case, I hope that the idea is quick. The idea makes sense. Yeah, so we found, we had to find a nice formula for theta. We found that tangent of theta was y t over x of t. That's SOHCAHTOA. Then we just hit both sides of that with arctangent. We took the derivative, which involved this fancy derivative of arctangent. along with the quotient rule, which helped us chain, and then we solved. All right. Phew, so a lot going on there. I think at least one of the following problems should be fairly short. So we will make up for that very long one. And again, no problem with me if we go a little bit over today. The next problem, I'll call it problem 3. I don't remember exactly which problem that previous one was, so I apologize. Problem 3 says find the area of the shaded region of the shaded region. Okay, we're given a lovely drawing. Okay, so it looks like we're going like this. We're going like shoop. Oh, that should not have that little thing at the end, like that. And then we're going to shoot down in a linear fashion. So it looks like kind of a quadratic function at first. And then we're going to shoot down and be all linear. Okay, so this is the area which we're interested in underneath this curve. Okay. And this curve is actually defined piecewise. So what we see is that this on the left-hand side here, we get y equals 4x squared. Okay, so that gives us this curve. Let me shift over to a different color. And then for this linear part down here, this is y equals 32 minus 8x. Okay, they give us the height of this point here. This point is 16. And they give us the x-coordinate as well, so this is 2 down here. So let me try to sketch that so that you can see where it lines up. And that point there is 4, and this, of course, is the origin. Okay, so it's good to know that if I don't get my PhD here, I certainly have a career as an artist waiting for me. So the way that we're going to find the area, we'll recall that the area under area enclosed, or how about this way, area between a non-negative function. Things get slightly more complicated if things get negative, just because we're going to have to worry about canceling areas and stuff like that. But if we have a non-negative function, the formula is nice and simple. Between a non-negative function, f of x, and the x-axis over the interval, say, a to b. This formula, very straightforward. All that we have to do is we have to integrate from a to b our function, f of x dx. Now in this case, we have these two functions. So what I'm going to do is I'm going to find the area. So let me call this area A1. You don't have to write out all of this if it makes sense to you intuitively, but just to kind of be clear about what I'm doing. So the total area in this case, total area is going to be A1 plus A2. Right? It's the area on this first half plus the area on the second half. Well, A1, we can see, I'll just write total area for TA for total area, not TA for teaching assistant Bailey. So this is going to be area 1 plus area 2. Well, area 1 is just going to be, it looks like we're going to want to integrate 4x squared, because that is our function. And we're going to want to integrate from x equals 0 to x equals 2. Okay, so this is going to be the integral from 0 to 2 of, what was our function again? 4x squared of, 4x squared dx. Okay, so this is a1 right here. Plus, now we're going to want to integrate the other part, which goes from x equals 2 to x equals 4. and that is 32 minus 8x. 32 minus 8x dx. All right, so this is a2 over here. And now we're just going to integrate and add them up. Okay, so the integral of 4x squared, well, we can bring that 4 out front if we want. I don't think in this case it really matters. Whenever I integrate this, I'm going to raise the power of x by 1, so now I have 4x cubed. And remember, I divide by my new exponent, which is 3. And I'm going to evaluate this from 0 to 2. Right, those are my bounds. Now the second one, this will be another application of the power rule. Remember 32, that's just 32 times x to the 0. So if I raise that power by 1, then I will get 32 times x to the first over my new exponent, which is 1. Yes, we will get rid of that shortly and just write that as 32x. The 8x, that's going to be minus 8x squared over 2. And we want to evaluate this part from 2 to 4. Okay, so let's go ahead and start evaluating this first part. That's going to be 4 times 2 cubed. 4 times 2 cubed over 3. Remember, whenever we evaluate, we plug in the top bound, and then we subtract out whatever we get from the bottom bound over 3. The second part, let's go ahead and before we plug in, let's make this easier on ourselves and rewrite this. Minus 4x squared from 2 to 4. Okay, so next step, we'll plug stuff in there. This one comes out to 32 over 3. 2 cubed is 8, so this is 32 over 3. I'll go ahead and write minus 0, right? 0 cubed is 0, so the second fraction is 0. Okay, so now plus, okay, first let me plug in x equals 4, and I get 32 times 4 minus 4 times 4 squared. Now minus, okay, 32 times 2 minus 4 times 2 squared. All right, so we'll have to work all of that out. This is equal to 32 over 3. I can get rid of that 0. Plus, okay, 32 times 4, that's 128. 128 makes another appearance in our video. Minus 4 times 16, it looks like, because 4 squared is 16. Minus, okay, 32 times 2 is 64. 2 squared is 4, so it looks like it's minus 4 times 4. So 32 over 3 plus, see, 128 minus 64. Minus 64 minus 16. So this is 32 over 3 plus 64 minus 48. Oh, no. And that is 32 over 3 plus 16. So that's 32 over 3 plus 48 over 3. And that is 80 over 3. And that gives us our area. All right, so again, this is very similar to problems which we have done before whenever we compute areas. The main difference here to kind of a standard area problem is that we need to add up these two separate intervals because we're given two separate functions for these two pieces. Okay. But other than that, things shake out pretty much exactly as you would expect. All right, so that puts us halfway done in terms of problems, probably more than halfway done in terms of time. Let me get to the next problem. Oh, that problem, I should jot it down for you, shouldn't I? This problem was 5.6.58 if you're interested, 5.6.58. Okay, so now I'm going to go find my next problem. I cannot believe we only have 3 more of these videos, including today. Okay, so what are we on? Problem 4. So problem 4 says determine if the following piecewise defined function, piecewise defined function is differentiable at x equals 0. Okay, so the function is f of x equals, is piecewise as promised, 4x minus 5 for x greater than or equal to 0, and x squared plus 4x minus 5 for x less than 0. And they actually guide us through this. So the first part, they don't call it part A, but I'm going to call it part A because I think it will make it easier to talk about. Asks, what is the right-hand derivative of the given function? Right-hand derivative of the given function. Okay, so what we want to compute is the limit as h approaches 0. We're going to go from the positive side because we want the right-hand derivative of f of 0 plus h minus f of 0 over h. Okay, you'll recall this is the derivative formula. This is the official definition of the derivative. I think that we might have written it slightly different in the past, but it's the exact same thing. And I think what we would have done before is we would have just put h minus 0 down here. But of course that is just equal to h. So, all right, well, let's go ahead and compute this thing. So f of 0 plus h, well, 0 plus h, I notice, is going to be greater than or equal to h, or excuse me, greater than or equal to 0, which means that f of 0 plus h, we're going to have to use this first definition, this 4x minus 5, because because 0 plus h is greater than or equal to 0. So it's going to be 4, 0 plus h minus 5. Okay. So what we want is we want the limit as h goes to 0 from the positive side of 4, 0 plus h minus 5. Well, that's just 4h minus 5, isn't it? Yeah. So this is going to be 4h minus 5 minus f of 0. Okay, well, f of 0, I can plug it into either one of these formulas and I will get the same thing. We should technically use the first formula because that one says x greater than or equal to 0, but really they'll both work in this case. Regardless, we see that f of 0 is negative 5 because if I plug in x equals 0, then I get f of 0 equals 4 times 0 minus 5. So minus negative 5 over h, okay, equals the limit as h goes to 0 from the positive side. Okay, well, this comes out to 4h minus 5, and then minus a negative 5 gives me a plus 5 over h, equals the limit as h goes to 0 from the positive side of 4h over h. And that comes out to just be 4, because the h's here are going to cancel, and then this is just the limit of the constant function 4. So here it didn't actually matter that we were taking the limit as h approaches 0 from the positive side. Excuse me, yes it did. It did because whenever we did 0 plus h here, if h was negative, then we would have had to use the other function. We would have had to use the x squared plus 4x minus 5. So actually, we did use that fact. All right, let's jump to part B, which is very similar. What is you guessed it, now they're asking for the left-hand derivative of the given function. Derivative of the given function. So this time, very similar setup, but we're going to look at the limit as h approaches 0 from the left, so we're going to give it a negative sign. And again, we have f of 0 plus h minus f of 0 over h. Well, we already computed f of 0, right? So we're not going to have to compute that again. However, in this case, so 0 plus h is going to be less than 0. And this is because we're assuming that h is less than 0 because we're approaching from the negative side. Okay, so let me draw that to the negative arrow to be clear. That's because we're approaching from the negative side. So this means that f of 0 plus h equals, I'm going to have to plug it in to the lower formula now, x squared plus 4x minus 5 equals, so 0 plus h squared minus 4, 0 plus h minus 5. Well, this just comes out to, it looks like we're going to have to do some ugly multiplication, but since we just have 0 plus h, this just comes out to h squared minus 4h and minus 5. All right, so let's go back and plug that into our, what we want, this limit. So we get the limit as h approaches 0 from the left-hand side. F of 0 plus h, we just computed that to be h squared minus 4h minus 5. Minus f of 0, you'll recall from before, was negative 5 over h. Okay, equals the limit as h goes to 0 from the left. Well, this is going to be h squared minus 4h minus 5. And again, we're going to do a minus. We're going to get a plus 5 all over h. Equals the limit as h approaches 0 from the left of just h squared minus 4h, because I've got a minus 5 plus 5 over h. Well, now I've got h's all over the place, so I can cancel some, and I get h minus 4. All right, I've canceled the h's everywhere. And this, it looks like, is going to be negative 4. Because now we can just plug in h equals 0, and we get negative 4. That brings us to part C, which really gets at what the question was originally asking. And this is just a simple yes or no. Is the given function differentiable at x equals 0? Well, we see that the limit, whenever we approached from the left-hand side, we got negative 4. And whenever we approached from the right-hand side, we got positive 4. So what that means is no, this function is not differentiable because the limit as h approaches 0 from the positive side of f of x plus 0 plus h minus f of h minus f of 0, 0 over h is not equal to the limit as h approaches 0 from the left of this thing, 0 plus h minus f of 0 over h. Okay, so if it were differentiable, those two things would certainly have to be the same. That's because for it to be differentiable, this limit as we approach 0 would have to exist, and the limit does not exist if we get two different things whenever we approach from the left and the right. All right, next up we have problem 5. This is one which I believe I've done 2 times before, so I'm excited to revisit it for a 3rd time. It's a tricky problem, so I don't say that to mean like, stupid, you couldn't solve. No, this is a tricky problem. I'll admit it's one that I find challenging, so definitely good to revisit it one more time to get you prepared for the final. Problem 5 says to graph the following function. I think that you'll probably recognize it once I write it all out, or once I start writing it. Not by plotting points, but by starting with the graph, of y equals the square root of x, and applying an appropriate transformation. All right. So the function which we're given in this problem is y equals negative root 3x plus 2. Okay. So the way that we want to get started is we are going to rewrite this. So rewrite as y equals negative. Now what I'm going to do is I'm going to factor 3 out of both of these under the radical so that I get 3 times x plus 2/3. The nice thing about this is that it allows me to see this x plus 2/3. That's going to be important whenever we are going to look at how the graph has been shifted. So it kind of gives us some blanks here. So let me kind of write out what those are to guide us. So it says compress. The black that I'm going to write here is going to indicate what is given to us, and I'll try and make the blanks clear. Compress the graph of y equals root x, and then we have to fill in the blank. We have to determine whether this thing is being compressed vertically or horizontally. Well, since we have a scalar in front of the x here, we have this 3 here, and 3 is bigger than 1. I should use a different color, shouldn't I? This means that we're going to compress the graph horizontally. Okay, let me emphasize again, this is because we are multiplying x by some k greater than 1. Okay, in this case, k is just 3. Okay, so we have this 3 out front of the x. So that tells us that we're going to be compressing it horizontally because they're messing with the x here. By a factor of, you guessed it, since this coefficient is a 3, we are compressing it horizontally by a factor of 3. Okay, so that just goes back to the same point. Then shift the graph to and I think, yep, there's a blank here, and it's either left or right. Are we going to shift it to the left or to the right? This is that weird thing where, since I have x plus 2/3, so the rationale behind what I'm about to write here is because x plus 2/3, and it's really this plus 2/3 that's important. it's this funny thing where plus 2/3, you would think we're moving further in the positive x direction, but actually we're shifting it to the left. We're moving more negative to the left. To see why this is true, if we look at, for example, just if we were to ignore the plus 2/3, then the thing that would then, how do I say this? I think that the best way to see this is to play around with it a little bit yourself and plug in some points. So I'll encourage you, let me give you a few points to look into. So plug x equals, we'll say minus 2/3, 0, and 2/3 into both, and we'll keep it simple actually. I'll just say y equals root x into both y equals root x and y equals root x plus 2/3. It's one of those phenomena that's difficult to explain, but I think that if you play around with it a little bit, you will get comfortable with it and make more sense of it. So plug a few points into these things and compare the graphs, compare their values, and I hope that you can kind of start to see why that is. So the left, by, and now there's a blank again, how many units? And since we are shifting it, we have this 2/3 here. We are going to be shifting it 2/3 units to the left, okay? Again, that's why it's important that we factor that 3 out at the beginning, because otherwise, if we had a 3x, then the shifting would be a little bit more foggy. But by pulling that 3 out, we can clearly see the shift. Finally, we are then going to reflect it, and then reflect it about the blank axis. Oh, I guess it doesn't say axis, but both of the answers have axis in them, so that's okay. So are we going to reflect it over the x or the y axis? Well, since we have a negative out front here, we have this negative out front of the square root. What that means is that, well, again, perhaps the best way to see this is to plug in a few points. So whenever I plug in, if we ignore the negative, the negative, all that it does, let's say that we got 1 as our value under the radical. Well, the negative is going to send that point to, so the negative sends the point xy to the point x negative y. Again, I think the best way to see that is to play around with it a little bit. But regardless, the negative out front is going to reflect this over the x-axis. I should have written that in blue to be consistent. So if you want to make a very quick sketch of what is going on here, very, very quick. Okay, so this is y equals root x. It looks something like this. Y equals root x. And now let's look at the changes that we've made. Compress it horizontally. Okay, well, I'm not very good at drawing that. But we compressed it horizontally. We shifted the graph to the left. Okay, so we took it and we moved it over to the left by 2/3 units. So we brought it over here. Let's mark this as like 1. Oh, that's not 2/3 then. Oh, this is, okay, let's make this 1. And let's make this 2/3. Okay, so we shifted it over 2/3 units. And instead of going up and to the right, since we reflected it across the x-axis, we're going to come down and to the right. Okay, so this is a rough sketch of y equals negative root 3x plus 2. And we didn't have to plug in a single point. All that we did was made a couple of changes to this original graph. Okay. The best thing that I can encourage you with regard to those functions, those examples, is to practice, play around with some functions, and you'll get the feel of it, I think. That's how I have gained an understanding. And even I still need to play around with these things quite regularly. All right, so final problem of today's review, problem 6, says find the open intervals. Actually, there are 2 parts, and it jumps right into part A without any lead-in. Find the open intervals on which the function, so we have h of x equals x cubed minus 4x squared is increasing and decreasing. Increasing and decreasing. So another way of writing this would be asking, where is h prime of x positive and where is it negative? Where is h prime x greater than 0 and where is h prime of x less than 0? That would be another way of writing this problem. So the first thing that we're going to want to do is compute h prime. Thankfully, this is a nice polynomial, so its derivative is fairly straightforward. We can apply the power rule, so we get 3x squared minus 8x, right? Bring down the exponent, so 3 times x, and then we lower the exponent by 1, so that gives us x squared. Okay, so we've got h prime of x. Now, we want to find the critical points, which you will recall is where is h prime x equal to 0 or undefined, right? Where does it break? Well, it's defined everywhere, so I don't think we're going to have to worry about that, right? No matter what I plug in for x there, I'm not going to be dividing by 0, taking the square root of a negative number. Everything's going to be perfectly legal. So it's defined everywhere. So we have to find where the derivative is equal to 0. So I'm going to set 0 equal to 3x squared minus 8x. Okay, well, this is the same as 0 equals x times 3x minus 8, which means that either x equals 0, so x equals 0, or 3x minus 8 equals 0. Well, this is the same as 3x equals 8, and that is the same as x equals 8 over 3. So we've got our 2 critical points. So critical point and critical point. So what I'm going to do now, and there are different ways of organizing your information, but the way that I like to do it is with my little number line. And I'm going to plot my 2 critical points. So let's put 0 here. And let's put 8/3 here. Okay. So what we're going to do now is I'm going to find f prime of x. I guess h prime, because we're dealing with h here. So we got h prime of x, and I want to check each of these intervals. But so the interval less than 0, between 0 and 8/3, and from 8/3 to infinity. And I'm going to plug in a point from each interval. And what I'm particularly interested in, I don't care exactly what the value of h prime is, but I'm going to care if it is positive or negative. So first, I'm going to plug in a point to the left of 0. Let's go with -1. That seems like a nice one. I'm going to plug that into h prime, and I get, looks like 3 times -1 squared minus 8 times -1. And that, it looks like, is 3 plus 8, and that is 11. And in particular, What I care about is that it's greater than 0. So I'm going to put a plus here to indicate that the derivative is positive over that interval. Next, I want to look at the interval from 0 to 8/3. I'm going to plug in 1 to hit that interval. And so that derivative is going to be 3 times 1 squared minus 8 times 1. That's 3 minus 8 is -5, which is less than 0. So I'm going to put a minus here to indicate that the derivative is negative there. And finally, I need to look at things bigger than 8/3. Well, I could compute that 8/3 is just under 5, but I'm feeling lazy. So I'm just going to, or I could plug in 3 because 3 is really close, right? 8/3 is just barely under 3, but I'll plug in 5 because I know 5 is bigger than 8/3 if I was feeling lazy and didn't feel like computing 8/3 exactly. So h prime of 5 is 3 times 5 squared minus 8 times 5. Okay, so that's 3 times 25, that's 75, minus 40, and that is 35, which is certainly bigger than 0. So the derivative is positive over this interval. So now what I can say is that h prime, so h is decreasing. Remember, h is decreasing wherever the derivative is negative on the interval from 0 to 8/3, right, from 0 to 8/3. We don't include the endpoints because at the endpoints the derivative is 0, so that it's not neither increasing nor decreasing. Now technically I think you can include them and it's technically okay, but really it's not neither increasing nor decreasing there. And h is increasing, so this is just where the derivative is positive. And in this case, it looks like we're going to have a union because we have everything from -infinity to 0, -infinity to 0. But then we also have, remember the union just means I've got these two separate things. It looks like we also have 8/3 to infinity. So this gives us our solution to part A. Again, the question, where is h increasing and decreasing? That's the same as the question, where is the derivative of h positive and where is the derivative of h negative? Now let's move on to part B and identify the function's local and absolute extreme values. Functions local and absolute extreme values, if any. Remember, it is possible for there not to be local or absolute maxes and mins, if any, saying where they occur. A perfect example of that, by the way, would be a line. If I look at a line that's non-horizontal or vertical, so like y equals x, well, it doesn't have any local maxes or mins because it's always increasing, right? So like no matter where I look, I can always find a point. So if I sketch that real quick, y equals x, oh boy, let me at least make it go through the origin. Right, like let's say I wanted to say that this point was a local max. Well, clearly it's not a local max because if I go just a little bit to the right, I'm already going to be higher up. But it's also not a local min because if I go just a little bit to the left, I'm going to find something smaller. So it's not, so there are no local maxes or mins because I could say the same thing about any point on this line. And there's no global maxes or mins because the function is defined over all real numbers. So it's constantly changing. So that would be an example of a case that has no local or absolute extreme values. Anyways, that's not the function that we're dealing with here. Here, the function that we're dealing with is h of x. So what we can see immediately is that, so if I can see that the derivative is increasing, so the function is increasing until 0, then it is decreasing, and then it is increasing again. So if I were to sketch this very loosely, I'll just do it right here. It's going to be a mess, but you'll get the point. So the function is increasing here until 0, then it's decreasing. It shouldn't have that little hump there. It should just be decreasing, and then it starts increasing again. And so kind of intuitively, we can see that it looks like I'm going to have a local max there and a local min there. And indeed, that is the case. So we see that we have a local max at x equals 0, and that is because h prime of x is greater than 0 immediately to the left of 0, immediately to the left of 0, and h prime of x is less than 0 immediately to the right. Okay, does that make sense? Okay. Now, to find the specific value, we should plug in x equals 0 to find what the actual max is. So plug in x equals 0, h of 0 equals, I think it's a 0. Where is h of 0? Or h of x? There it is. H of x is x cubed minus 4x squared. So yeah, if I plug in 0, I'm going to get 0, which means local max at 0, 0. Okay, now similarly, we have a local min at what value was it? So if you look at this quick picture that we sketched, we see that right here at x equals 8/3, it looks like we have a local min because the function is decreasing to the left of that point, and then it starts increasing again afterward. So we have a local min at x equals 8/3, which means if we plug that in, local min at, h of 8/3 equals, oh boy. I might do this in my head right quick because this is going to be ugly. Where'd it go? Where'd it go? There it is. Okay, I'm not doing that. Never mind. No, I can do that. 64/9. Because I can factor out x squared. Let me see. So I get 64/9 times 8/3 minus 4. So that is 64/9. 8/3 minus 12/3. 64/9 times minus 4/3 equals negative. I want to say that's, no, it's 256. Negative 256/27. There we go. It's okay. I think that you could probably leave it, or if you have your calculator, you can do that. This was negative 256/27, and it's also possible that I made a mistake there. So don't bet your life on me there. But in any case, we now have our local max and our local min. Now, what about absolute maxes and mins? Well, if I look at my function, so my function is h of x equals x cubed minus 4x squared. Well, I can see that as x goes to negative infinity, this thing is going to shoot off to negative infinity because the x cubed is going to dominate the x squared. And whenever x is negative, x cubed is negative. So this will shoot off to negative infinity in the left direction and positive infinity to the right, which means there are no absolute maxes or mins. So no absolute max or min because the limit as x approaches negative infinity of h of x equals negative infinity, and as we approach positive infinity, we approach positive infinity. Right, so that tells us that a very rough sketch of our picture might look like this. So it looks something like this. Like it's shooting all the way down to infinity, and then up here it's at 0, 0 we have this local max, then we shoot down here to this local min, and then we shoot up to infinity, and we just keep going forever. So there's no absolute max or min, because we can always find something bigger or smaller. Okay, so that does it for this final exam review. I hope that you have found it to be helpful.